Hi everyone, this will be your video for continuity and end behavior. So make sure as you're going through here, you're taking notes, pausing the screen as you need to. There's a lot of important information in here that you're going to need to write down. So let's start with what continuity is. So hopefully you can see that base word in there, that we can understand that the word continuity is going to talk about when something is continuous. So we'll be able to say that a function is continuous, and now we're going to be able to prove that mathematically. So there's three things that need to take place for us to say that something is continuous. So the first thing that needs to happen is that our function is defined at C. So basically what's that saying is that you can have a point there. You have some point at f of C. It exists. It's on your graph. You can see it. The second thing that needs to happen for us to say that a function is continuous, this is where things get a little weird, so don't freak out yet. But the second thing that needs to happen is that it needs to approach the same function value from the left and the right side of C. We're going to use this notation that's called our limit notation, and basically we have to say that the limit exists, meaning that as we're approaching from the left and we're approaching from the right, we're approaching the same value, the same f of x value. Now, to kind of wrap that up, in our third step, whatever value we get from step 2 and whatever value we find in step 1 where our point is actually at, they must be equal to each other. So we need to make sure that f of c exists. We need to make sure that the limit exists, meaning that it's approaching the same value from the left and the right, and that we need to make sure that those two values are equal. So sometimes those three facts fail us, right? Sometimes we do have a point that exists, we do have a limit that exists, but they might not equal each other. So we have a couple different types of what we can call a discontinuity, or just a function that's not continuous. So a discontinuity, we have three different varieties, and we're going to break them down right now so that we can see the differences here. So our first type of discontinuity is an infinite discontinuity. So as you might have imagined, this means that there's going to be something that's causing our graph to go to infinity, or there's an infinite number of points in the difference here. So think of it as something going to infinity. So generally, if you have a vertical asymptote, that's generally going to cause us to have an infinite discontinuity. As you can see in this rational function that I just drew down here, our functions are going to infinity. They're never going to connect to each other. They're never going to reach a point where we can hop from one piece to the next. You can always visualize yourself as a little man walking along your graph. And as we're walking along, we get down here, and there's really no way that I can ever get to this next part of my graph. So there's no way that he can get there. That means that this is an infinite discontinuity. Our second type of discontinuity is a jump discontinuity. And a jump discontinuity kind of pretty much describes itself in the name here. So a jump would be something, if you would see, maybe we just had a horizontal line here, and then all of a sudden our line continues up here. So that would be a jump discontinuity. Again, if you had your little man, as he's walking left to right on your graph, there is no way that he is going to be connected to that second piece. So that is a jump discontinuity. And then the last one, which is a point discontinuity. And again, hopefully these names are pretty descriptive and they help you really understand when you're labeling the types of discontinuities. But a point discontinuity is just that. It's just one point is missing. This is what's called a removable, because you can just remove one point, replace it back in, and now it's continuous. So an example of that would be, maybe we have an absolute value function, but up here we have a hole in our graph. Now that doesn't necessarily mean that that point isn't there. Maybe it's somewhere else on this graph for us. That's a point discontinuity. Again, imagining your little man. He's walking along your graph, and he's going to reach just one single point where he can't get across to the other side. So again, we have our infinite, where generally you'll see a vertical asymptote. We have a jump discontinuity. Generally, this is more like a piecewise function or step function, most likely piecewise. And then we have our point discontinuity. This is probably the most frequent one that you'll see. Point discontinuities, these occur a lot when you are given a rational function and you can simplify it a little bit. So point discontinuities, one point is missing. It may be somewhere else on the graph, so always keep that in mind. Okay, so we're going to use our 3 ideas for continuity, and we're going to determine whether or not these functions are continuous. So these are both done out for us, so we're just going to kind of like go through, see what our process is here, and then we'll do our own examples on the next slide. So on this page, you can see that we have we'll just look at A first. We have a function, right? This is the function 2, absolute value of x plus 3. Now they also give us this specific x value of 2. So what we need to say is, okay, first, can I plug 2 in? Will I have a point? And you can try it, you can plug it in, and you get it. You do have a point when you plug it in. F of 2 is 7. And you get that just by plugging in 2 into your x here. So it would look like, I'll just do it in the middle, 2 times the absolute value of 2 plus 3, which is 4 plus 3, which is 7. So it does exist, you can get a value there. So that's kind of like your first check mark. So now we go on to our second task here, and we need to say, okay, is what value we're approaching from the left the same as the value that we're approaching from the right? So to do this, what we need to do is we can set up 2 little tiny tables here. And in these tables, we need to find values that are extremely close to 2. So you can see right here we have like 1.9, 1.99, 1.999. We're getting closer and closer and closer to 2 from the left. Now personally, you can also draw this like as a horizontal table, which might help you visualize like getting closer like in terms of like a number line. But really, however you want to set it up, whatever works for you, just do it. So using a calculator, you can plug in these numbers. So you would plug in 1.9 and we would get out 6.8. Now 1.99 is a little bit closer. We plug that in and we get out 6.98. Then we plug in a number that's a little bit closer to 2. Remember, we're trying to get to that x value of 2. And then from there, you can see that we're getting a little bit closer and we have 6.998. Now over here, we also have another table, and in this table, we're getting closer and closer to 2 from the right side. So we're starting at 2.1. That's pretty close, but we can get closer, 2.01, and we can get even closer, 2.001. When you plug those values in, you can see your outputs here. We're starting at 7.2. When we get a little bit closer, we have 7.02, a little bit closer, 7.002. So you can hopefully clearly see the trend here that this is getting closer to 7 as we're coming from the left, and this is getting closer to 7 as we're coming from the right. And the fact that they're both getting close to the number of 7, that's what means that's what our limit is. When they're the same value, then we can say our limit is going to equal that, 7. So that equals 7. So that's like our second little check mark here. The second thing that needs to be true for this to be continuous. Now the last thing is always the easiest, and all you need to do is to compare your value from your first check mark to your second. And if you look down here, we already have it written out. This was what we had from our second check mark. The limit was 7. Our first step, we found that f of 2 was 7, and this is great because these are the same value, which means that this function is continuous at 2. So I know that's a lot to take in. We'll be doing one totally out together, but I do suggest writing everything down on this page because having more examples will help you succeed. So let's look at this other example that's already done out here. So they're asking us about 1. So when we look at 1, and I just try to plug this in immediately. So if I come over here and I'm like, okay, I'm going to find f of 1. I have 2 of 1 over 1 squared minus 1. So as you might be able to see here, you're going to end up with 2 over 0. And that's not a good number, right? That's not a real thing. We can't divide by 0. This is a bad thing happening to us. We don't have a point at 1. So that means that our function is not defined at 1, which is actually already written out down here. So it's not defined at 1 because we have 0 in the denominator. We can't divide by 0. So right there, we can pretty much say that this is not going to be continuous. You can see here that on this example, they still try to show you that, okay, as we're approaching 1 from the left, we're getting closer and closer to 1. We're getting a much larger and larger negative number. So you can assume this is negative infinity. As we're approaching 1 from the right, so we're getting closer and closer to 1, we're getting closer and closer to bigger numbers, so positive infinity. This is a great way to tell that when these are pretty much exact opposites, this is an infinite discontinuity because there are so many steps in between our two values here. And you can assume that if you plugged in a number closer to 1, it's going to be a bigger negative number. And if you include a number closer to 1, it's going to be a bigger positive number. So negative infinity, positive infinity, definitely not the same, but it does let us know that we have an infinite discontinuity. Alright, so here we are with our own examples here, and we're just going to look at number 1 to get started with. So we want to figure out if this is continuous by using our continuity test, and if it's not continuous, we just want to figure out what type of discontinuity do we have. So let's start with our first test here, our first piece of our test. Does f of 2 exist? And I chose 2 because that's the x value that they're asking us for. So does f of 2 exist? Can I plug it in? So f of 2. Be very careful with piecewise functions here. It does depend on this criteria. So we're looking for f of 2. We would use this piece if we were trying to find any number greater than 2, and we'll use this piece for any time we're using any number less than or equal to 2. So equal to 2, this is the piece we're going to be using here. And we know that this is going to be 2 minus 1 because I replaced x, which is 1. So f of 2 is 1. It exists. We're good to go on that part. Now let's talk about our second criteria. Does the limit exist? So does the limit as x approaches 2 of f of x exist? So the way that we do that, we're going to find the limit approaching from the left, we're going to find the limit approaching from the right, and then we're going to see if those equal each other. If they do, then our limit exists. So let's, I'm going to show you the horizontal method for the table here. Alright, so it's still an input-output table, but now it's going to be horizontally. I need a little more space there. Alright, so I'm going to put 2 smack dab in the middle. And I don't know what's going on there, so there's a question mark. So this is going to be our x, this is going to be our f of x. Now you can think about this a little bit easier this way because you can visualize, you know, a number line. So if I were to think of the number 1.9, I could get a little bit closer and do 1.99, and I can get a little bit closer and do 1.999, squeezing it in there. So now we can go in the opposite direction. It is a little bit tricky when you're coming in from the right because the numbers are going to be greater than the number you're looking for. So this would be like 2.001, 2.01, and then just a little 2.1. I personally prefer this method a little bit better just for myself because I like to see right here, these are the two values that we're going to be comparing, and they're pretty close to each other, so that's good. So one thing that's special with this problem specifically is that it is piecewise. So when we're looking here, we have to make sure that we're using the right piece of our function. So as we're coming in from the left, for all the values less than 2, this is the piece we're going to be using. So just for myself, I'm going to be writing it above those pieces. Oops. We'll make that your x minus 1 pieces. And then for our second side over here, the right-hand side, those are the values greater than 2, so we're going to be using that piece, the 2x plus 1. I know this is a little confusing because not only are you learning this for the first time, There's like little extra hard pieces going on here, but it'll just make you a stronger student. So when we're plugging in these values, you can just use your calculator. My biggest thing is do not round your decimals. They are important. So you can just plug them in. We're going to get the values, and then we're just going to compare. Are they approaching the same value? So on my left-hand side, when I'm plugging in 1.9, I'm going to have 0.9 as my result. 1.99 will give me 0.99. 1.999 will give me 0.999. All right, so you can kind of see what value they are approaching. Now we can look at our other side. All right, so now on our right-hand side, we're going to be plugging into our highlighted red function. This is because this is piecewise. It is a little bit more confusing, but remember, just take your time. So when I'm plugging in 2.01, I get 5.002. When I plug in 2.01, I get 5.02. And when I plug in 2.1, I get 5.2. So hopefully, when we're looking at these two numbers, we do usually hope that they are the same, but you can clearly see that they are not the same. From the left-hand side, the way that we could write this out, okay, so just go with the notation here. So the limit as x is approaching 2. Now when we're talking about left-hand side, we have a little minus. So the left-hand limit, that's going to equal 1. We're approaching the value of 1. Now when we're looking at our right-hand side, we have the limit as x is approaching 2. We use a little plus sign to talk about the right of f of x. And you can see that that number is getting closer and closer to 5 as we're coming in from the right or as we're coming in from the left. So this is a pretty big issue because 1 does not equal 5 in my book, right? 1 does not equal 5. So this tells me that the limit does not exist. So that's a bad thing for us, right? So the limit doesn't exist even though that there was a function value there. That's going to happen, right? This is going to tell us that this is a non-continuous function or discontinuous function. And this can also tell us that it'll be jump, right? This is a jump discontinuity. And it's a jump discontinuity because if you think about it, we're just jumping from the value of 1 to the value of 5. So this is a jump discontinuity, jumping from 1 to 5. So again, this is discontinuous. We'll do the final answer in red. Okay, so 3. So the limit didn't exist, so we can't even say that it's going to equal. So this is discontinuous. So a discontinuous function. And we know that because we went from the values of 1 to 5, this is a jump discontinuity. Okay, so again, this is discontinuous, and I'm going to scroll this up so we can write why it was discontinuous. Okay, and that's because the limit did not exist. So remember, if you think back to those 3 things, you need to make sure that the function value exists, the limit exists, and that they equal each other. And this one clearly did not. So I am going to show you one more example on this page, and I promise this one's going to be a little bit easier. So that'll be nice, and I'll show you how it works out nicely. So again, the first thing we always need to figure out, does f of 4 exist? Okay, so what does f of 4 equal? All I need to do is plug in f of 4. I need to plug in 4 here. So I'm going to have 4 squared plus 5 times 4 plus 3. It's going to be 16 plus 20 plus 3. So it's going to give me 39. It's a big number, but hey, it's real, so it exists. The second thing we need to find out, does the limit exist? So the limit as x approaches 4 of f of x. Does that exist? So again, we need to write that numerical table here. You know what? I'm going to write this underneath. We're going to do this one down here so we can do it horizontally. So we can set up our table. We're going to put the number 4 in the middle. We're going to pick values that are close to 4 coming from either direction. So coming from the left-hand side, we can start at 3.9, then we can do 3.99, and we can do 3.999, getting much closer to 4. And on the right-hand side, we could start at maybe 4.1, 4.01, 4.001. All right, so remember these are our x's, this will be our f of x. So this one's a lot simpler than the last problem because we just have one function that we need to plug this into, and we just need to make sure that after we plug it in, that these two values are pretty close to each other. They're approaching the same value. So again, just using your calculator or your graphing calculator, whatever works for you, plugging in these values. When we plug in 3.9, we get 37.71. When we plug in 3.99, we get 38.87. When we plug in our next number, we get 38.987. Should have left more space. There we go. And then when we're looking on our right-hand side now, when we plug in 4.1, we had 40.31. When we plug in 4.01, we have 39.13. And when we plug in 4.001, we have 39.013. All right, so this is nice, right? They're definitely both approaching the value of 39. So this is exciting. So yes, we can say that the limit as x approaches 4 because we can see that they're both approaching the value of 39 down here. F of x equals 39. So that's our second check mark. So this is great. So far we've passed our first two pieces. Now we just need to make sure for step 3, do these equals. So we need to make sure that the limit as x approaches 4 of f of x, we need to make sure that it's going to equal whatever f of 4 was. So just using the values that we found. So up here we found that the limit was 39, so we can say 39. And over here, we found that this was 39, so we can say 39. This should be exciting, right? So this is the same. So because they are the same, because this all works out, this is a continuous function. Okay, so because they are equal, this is continuous. You always need to make sure that you have some sort of statement to conclude your answer, okay? Just showing me the steps is not telling me anything. It's just showing me that you're finding some random stuff. Being able to put all that stuff together and get an idea out of it, that's what your answer needs to be. So you must have some sort of written explanation, not just work, not just showing me that you plugged in 4, but that you did figure out that these pieces together work to tell me that it is continuous. Okay, so we've worked with continuity. Now we can start talking about end behavior. And when we do this, I can promise you it's going to be a lot easier than continuity. So end behavior is just all about how the end of the graph works, right? Where is it heading? Okay, is it pointing up? Is it pointing down? So we do use some notation here. I do definitely suggest writing this down. The notation that we use is going to be a little bit more simplified than this. So when we're talking about the right hand side or the left hand side, you can just use like the words like right end or left end. And then so the way that we're going to write this out into words, so the right end, so as x is approaching infinity, meaning that it's going to the right of our number line. It's increasing, it's getting bigger. You know how your x-axis works. So as x approaches infinity, our left-hand side, our left end, would be as x approaches negative infinity. And then the second part down here, f of x approaches, this is the part that you're going to be filling out. So f of x approaches, and it's a blank there. So this is a great way if you know, when you're going through your work, if you like to just get it set up and then figure out, okay, what do I need to figure out? I need to figure out which way is my graph actually pointing as I'm going to the left, or which way is it pointing as I'm going to the right. So it'll always be set up like this, and then we're going to fill in those blanks. Okay, so always set up like this. All right, so now let's talk about what we can fill into those blanks, and we're going to do that with an example on the next page. So for instance, I have this function here. I'm going to do some right-hand side over here. So my right end, and then we'll do our left end setup over here. So I know that you can see as I'm going to the left, as I'm traveling along my x-axis to the left, so we're going to write as x is approaching negative infinity. It's getting smaller. Our f of x is going to approach what? And then for our right-hand side, we're going to be going as x is getting greater. So you can see as x is approaching infinity, f of x is approaching what, right? So the big idea here is if it's pointing up, that's positive infinity. If it's pointing down, that's negative infinity. And hopefully that should make sense, right? Up, positive, big numbers, positive infinity. Down is negative, little numbers, negative infinity. So that's all you need to do is just really look at your graph and figure out what do we need to fill into this blank here. So I just need to figure out it's pointing up, so that's going to be positive infinity, so I'm going to fill that in. And over here it's pointing down, so it's negative infinity in here. Now keep in mind, right now this is a coincidence that these values are the same. What I want you to remember is that everything that's in blue, everything that's in red will always be written like that. The only thing that's going to be changing is what's in this box right here. Okay, and they could be changed. This could be positive, this could be negative, they could both be positive. It could be whatever it wants to be, but everything that's in blue will stay, everything that's in red will stay, and depending on how your graph is pointing is what you'll fill in. Let me just show you one more example just to clarify that, and then you guys will be good to go. Okay, so here you can see we have a rough sketch of just another graph that we're going to determine end behavior, and we can get it set up. So we know our left end, we're always going to set it as x approaches negative infinity, f of x is approaching something, and we can get our right end set up. Same kind of idea, but now it's as x is approaching infinity, f of x is approaching something else. So what we can do is we can go and look at our graph now. So as we're going to the left, you can see that my graph is pointing downwards. So that means that as it's going to the left, it's going to negative infinity. All right, now we can go to the right-hand side. So as I'm traveling to the right, my right-hand end is also pointing down. So down is negative infinity. So just like I said, these can be the same, they can be opposite, they could both be positive, both be negative, they can be all mixed up, and that's fine, okay? Whatever's in blue and whatever's in red is what you set it up with, and then you can just fill in your answer into the blocks.